Yeah, no problem. Let's let's look at the results.
This meeting is being recorded.
So for now, we have just eigenmodes for one particular frequency, which is the central frequency, 300 terahertz. So what do we have? In 1D results, we have port information folder. This gives us some information about the eigenmodes of the port. Mostly we are interested in gamma. Gamma is basically the wave number. Well, more precisely, this imaginary part of the gamma is the wave number. So do you have the same results? So one of the modes should have propagation constant 2 times 10 to the power of 7. Yeah, okay, I think, yeah. So can you tell me which of these modes are guided and which are something different?
Yes, this one, the red one. Okay.
Why do you think so? Just intuition.
It's
Remember, we had this just last time, yeah, when we calculated dispersion of the waveguide, and we needed to make just a quick, maybe guess, is this guided mode or something else? So for any dielectric waveguide, you have two light lines, and the guided mode should be inside these two light lines. So the first light line corresponds to the free space radiation. So it's easy to find this. So if the frequency is 300 terahertz, then the wave number corresponding to the 300 terahertz, simply 2 pi multiplied by frequency divided by speed of light. So if you divide 300 terahertz by speed of light, you simply get 10 to the power of 6. So this means that the K0 in free space is 2 pi multiplied by 10 to the power of 6. 2 pi is 6.3 approximately. So where this K0 is, it's actually somewhere between the third and fourth modes. Yeah. So that means that all modes above this K0 are probably guided. So the second light line corresponds to the wave inside this dielectric material. So if n equal to 4, you simply need to multiply this wave number K0 by 4. So instead of 6.3, you get approximately 25. So all these first, second, and third mode, they are inside this region. So they should be guided. Of course, the first one, red one, yeah, it's it's closer to the second light line. So it's very well localized. It's fundamental eigenmode. The second and the third, they are quite poorly localized. Yeah, they're close to the first light line. So let's check the field distributions. So you can, in 2D, 3D results, you can open port 1 and, for instance, check electric field 1. So there you can use, instead of arrows, you can choose contour if it's more convenient. And also, if you choose contour, it plots real part by default, but probably maximum is the best option. So it's kind of amplitude of the field. So for instance, the first mode is localized very well, as we expected. If we look at the second, it's also localized, not that well, but still it's definitely guided mode. The third one also seems fine. Although, well, you can already see that it's localized more and more poor. And if you open force mode, you can see it's not guided mode. So it's already the mode of the waveguide port itself. So even if you remove dielectric, you still have hollow metallic waveguide, which supports eigenmodes. But they have wave numbers lower than K0. So this is what you see. So actually, first three modes are fine. And we needed only first two. So just because we have this task. And because you see that the third mode is very close to the to this K0, so to the light line, that means we work almost near the cutoff frequency of the third mode. Yeah, we're slightly above the cutoff frequency of the third mode. Okay. So that's why we actually chose this frequency range from 180 to 280. Because if we go above 280, there appears third mode, and we don't need this. So now let's make a sweep. So go to Home tab, Parametric Sweep, choose New Sequence, New Parameter, and we will change F0 from 180 to 280. And let's make, to save some time, step width 20 terahertz. After that, click OK and start simulation. So you should get the results in this frequency range. From 180 to 280 and step 20 terahertz. This flow is F0. Yeah. Step 20. Okay, yeah, okay. So you can open this gamma folder, choose all modes, and then you can see how these modes appear during simulation. So you can see there is the first mode. It's definitely above the light line, so it's very well localized. This is fundamental mode. Next mode actually has cutoff frequency maybe somewhere around 250, 260 terahertz. And the third one, basically the only point above the light line is the point 300 terahertz that we just seen. So all other modes, they are actually below the light line. So we are not interested in them at all. Okay. Now, I think you've got these results. So now let's just quickly look at the second step. I think we will not do this. We will not do it right now, but let's see the idea. So again, I will not go into a lot of details about this. So suppose you have a current source, which is dipole, point dipole, electric point dipole, that is placed near the waveguide. And the waveguide supports certain eigenmodes. So you can calculate the power that is coupled to this particular waveguide modes by using this formula. So this is called Fermi's golden rule. So you can calculate coupling between the quantum transition to an optical mode. It works with every optical mode. So for particular waveguide modes, the formula looks like this. So it has just certain constant. So you can neglect it. So it's just a constant. There's also group velocity and this expression in the numerator. So there is electric field of the mode at the point where we will place the electric dipole source. And we calculate dot product of this field with the unit vector of the dipole moment. So that means that in order to find this whole value, what we need is to find electric field. So electric field should be found at this particular point. So we need to calculate electric field at the point z equal to r plus z shift. And we need only Ex because electric dipole source will be oriented along x direction. So that's what we need. And so in this particular case, remember that once you have eigenmode field distribution, it's defined up to a constant, as all eigenvectors are. Yeah, they defined up to a constant. So you need to normalize it somehow. So in this particular formula, the electric field is normalized in the following way. Yeah. But in CST, normalized in a different way. So you need to add another constant. Some formulas written for this. So in the end, what you get is the following formula, which is rather simple. So you have this E squared, which you can get from the simulation, and some A, which is a constant, which you can simply calculate. This A actually, I think, there is a parameter in the parameter list that corresponds to this constant A. So let's find this Ex squared using post-processing templates. And after that, we'll first move to the third step, and then maybe if we have time, we'll finish this. So how do we find E at the point where the dipole source is located? So go to post-processing, result templates. There, in the first line, choose 2D and 3D results. And in the second line, evaluate field in arbitrary coordinates. Okay, so in the first line, you choose the field distribution. So we're interested in the first and the second mode, so we'll have to make separate post-processing step for the first and second mode. So right now, let's choose mode 1. So port modes, port 1, E1. Then what kind of component we need? We need X component because electric dipole will be oriented along it. And we need magnitude So this will be absolute value of this component. At which point, first calculation range, choose 0D, so single point. So x direction will be minus Lx over 2. It's where the port is located. Y direction is 0. And Z direction is R, radius of the waveguide, plus Z shift. Z shift is the variable that we have in parameter list. It's the shift of the dipole from the surface of the waveguide. So after you've done this, click OK and evaluate. Evaluate for all runs. So yeah, it cannot do this for all runs, unfortunately, because the program contains only the fields for the last evaluation. So we have only one value for now. So this will be a modulus of EX. So now, if you go to, again, this post-processing dialog box, in the first line, choose general 1D, and in the second line, mix template results. And there, so for instance, for A, you have this first calculation, first step, where you find absolute value of EX. So you can take, for instance, A squared. So this will be just absolute value of EX squared. So for now, we'll just leave it as this. So type there A squared, OK, and evaluate. Okay, so basically what we've done, we've calculated this part. So in order to calculate this power, normalized power per cell factor, so we need to multiply it by this constant. So for now, we will leave it because we need to make the third step. If we have some time, we will add this constant later. So now we move to the third step. So let's do the following. We will save this project as the new one, and we will make some changes in this second project. Okay, so now we're actually using the source, this point dipole source, quasi-point dipole source, in order to excite the system. And then using ports, we will collect the radiation and see how much power was channeled into the waveguide. So what we need to change here? So first, discrete port. This is the main thing. We need to add this discrete port, this quasi-point-like source. So let's first do this. So we go to folder ports, right-click, and choose new discrete port. In this discrete port, we need to set the, so this is kind of small piece of wire. So we need to set the length of this wire. So it should be quasi-point-like, so it should be much smaller than the wavelengths. So there is the variable LD, size of the discrete port. So we will use this as the size of the discrete port. So it's oriented along X direction. So as X1, we will type minus LD over 2. X2 will be plus LD over 2. And Z is equal to R plus Z shift. So this is the point where we want to locate it. So after you've done this, click OK. So now you should have this port. Okay, so let me open this once again. Yeah, so what we want to calculate is the power coupled to the waveguide modes, but it is normalized. Normalized by what? By the power emitted by the same source in free space. So we will need to create another project later where this source is located just in free space. In order to do this properly, we need to set local mesh near this discrete port. Otherwise, the result will be slightly inconsistent. So to do this, let's go to Modeling tab and create a brick. So this brick will be a small area around the discrete port. So the size of this brick will be equal to, let's say, 3 LD. Yeah. So, for instance, Xmix, actually, I think 2 LD is enough. So Xmin can be equal to minus LD, Xmax to plus LD. The same for Y direction. And the same for Z, but also you need to, in case of Z direction, you need to add R and Z shift. Yeah, so minus LD plus R plus Z shift. And material should be vacuum. You can click preview. There should be a small brick surrounding the discrete port. Yeah, is this okay? Any problems?
Plus I. Also, likewise, what you have.
Okay, now why do we need this brick? So it's made of vacuum, so we made no difference. But now, since we have this brick, we can set local mesh settings on this brick. So we go to the mesh view. So for instance, open Home tab, click Mesh View. Then choose this list of components, list of objects. Choose this brick. See, there is an option, Local Mesh Properties. So open this Local Properties. And there is a variable max step width. So this is the maximum size of the mesh cell. So put there 10 and click OK. After that, you can click Update to see what kind of mesh you have in general. So it should have quite rough mesh for the waveguide and very fine mesh for this brick. Choose all components and see this mesh. Okay, perfect. Now, what else? Yeah, we need to change something also. First, let's look at the symmetry planes once more. If we forget about the source for now, okay, we have only a cylinder. How many planes of symmetry cylinder has? Just a cylinder. All three, of course, yes. So if we look only at the geometry, we have three possible symmetry planes, and the type of the symmetry plane doesn't matter if we're talking just about geometry, not about the fields and so on. So that means that we could set all possible symmetry planes. But now we add a source. So first, this source is shifted in that direction. So it immediately breaks symmetry z equal to 0. So we do not have that plane of symmetry at all. And second, this source is the current source. So the current or dipole moment, it's a polar vector. It points along x. And that means that x equal to 0 plane can be only electric symmetry plane. Because current points normal to this x equal to 0 plane. So for the source, x plane should be E-type. And in the same way, y equal to 0 plane can be only magnetic type, because now current is tangential to the y equal to 0 plane. So the symmetry of the source is x plane E-type, y plane H-type. Yeah, and because our geometry has all possible types of symmetry planes, that means that in general in this model we can set symmetry planes according to the symmetry of the source. So x plane should be electric, y plane should be magnetic. So we already have. So you can open simulation, boundaries, symmetry planes. Y plane is already magnetic. So we just need to set YZ plane, so x equal to 0 plane, as electric one. Click OK. Now see, we have set, click OK. So we have set x equal to 0 plane. So that means that the program will only consider the upper half of this simulation domain. So right now we have kind of problems that the waveguide port that we have, it's located in the lower half, in the lower half, so for x, for negative x direction. So it won't be considered in the simulation. If we want to consider waveguide port in the simulation, and we want to do this because in this way we can easily find the power that is absorbed by the waveguide. So we need to go to this waveguide port, double click, and change orientation from positive to negative. Now the port is located on the X max boundary, and it will be considered in the simulation. Actually, I don't know, let me, looks a bit strange. No, I think it's fine. So there could be some bugs. So it can still show port on the left side, so for negative X, but it still should be on the, at the right boundary. Okay, so let's see. So we said symmetry plane source. So once we have waveguide port, the power will be calculated automatically. So I think we will skip this radiated power. So for that we need far field monitors, but forget about it. Okay, one more, maybe not super important, but let's go to the mesh view once again. Now we will choose waveguide object and also set local mesh for the waveguide. So again, we will click local properties, but now we will make maximum step width 50 nanometers. And click OK. Now the last thing we need to do is change the solver settings. So go to setup solver, open solver settings. So we need to make few simulation at specific frequencies. So we will choose discrete samples only. You probably have this option calculate modes only, so we remove this option. We don't need it. As a source type, choose port 2, the discrete port. If you have different number, choose this discrete port and click apply. Okay, we forgot another thing. So for now, we have a global frequency range from 279 to 281. Yeah. So let's change it from 180 to 280. And yeah, don't forget to click parametric update after that. Okay. After that, let's return to the setup solver. And we need to choose frequencies at which the simulation will be done. So in the second column, choose equidistant, number of samples 6. And you don't even need to define the frequency range. So if you don't change it, it will be the global frequency range. So you will have simulation for frequencies from 180 to 280, 6 frequencies overall, so 20. The very last thing, go to the specials, and there is an option open boundaries. So by default, it's usually this SIBC, scattering boundary conditions, which are not very good sometimes. So if you want better accuracy, choose PML. PML, click OK, and I hope that's it. You can click Start, and hopefully everything will be all right. We forgot important thing. Yeah, we forgot to change boundary conditions. The boundary should be actually open, all of the boundaries, because now we're actually considering the source that is in infinite space. So if you have some different boundaries, please change all boundaries to open.